We present an asymmetric contextual modulation for inference target detection. Here is some representative images. It can be seen that the inference targets are buried into heavy cloud in complex backgrounds. This field has two bottlenecks. First, so far we still lack a public dataset, which is an open benchmark that different methods can be trained, tested, and compared fairly. However, collecting real-world inference target images is extremely difficult. This is the main reason why we still lack such an open benchmark. Second, the inferred small target has minimal intrinsic information, significantly lacking texture or shape characteristics, resulting in a large contradiction between feature map resolution and semantics for deep networks. To solve the above issues, in this paper we first contribute an open single-frame dataset with multiple kinds of annotations. Second, we propose a specially designed symmetric contextual modulation module, which mutually exchanges high-level semantics and low-level fine details. Our dataset contains 427 images, including 480 instances, and has 5 kinds of annotation to support multiple tasks. In this dataset, about 90% of images only containing a single target. This fact supports many sparsity of salience-based methods. However, it should be noted that there are still 10% images that only contain multiple targets that would be ignored under such global unit assumption. Among all targets, about 55 targets only occupying 0.02% of the image area. Therefore, when designing convolution networks, the priority should be preserving and highlighting features of inference targets in deep layers. Last, we come to the statistics of the target brightness distribution. Note that only 35% targets are the brightest in image. Therefore, picking the brightest pixel or threshold in the image is definitely not a good idea. To better highlight small targets, besides a conventional top-down global contextual feedback, we supplement a bottom-up modulation pathway based on the point-wise channel attention for exchanging high-level semantics and subtle low-level details. This is a plug-in module which can be inserted into existing networks to increase the detection performance. In our work, we present 2 examples of host networks, namely feature pyramid networks and U-Net, to obtain our ACM-FPN and ACM-U-Net. This is the backbone we used for experiments. We conduct a detailed ablation study by keeping the same parameter number. From the details, it can be seen that a smaller downsampling rate generally has a better detection performance, especially as the network goes deeper. By comparing the top-down local and bi-local, it shows that it is better to use bidirectional attentional modulation instead of the top-down modulation only. By comparing bi-global, bi-local, and the proposed asymmetric scheme, its results verify our hypothesis of the proposed asymmetric modulation. That is, top-down modulation needs a global channel attention module for the high-level symmetric information of the full image, while the bottom-up modulation requires a point-wise channel attention module for the low-level fine details. We also compared our network with other models. From Figure 3, it can be seen that the proposed ACM module host networks can gain a large performance boost even with few layers of parameters per network. Not only related to deep learning approaches, our proposed networks support the traditional modern driving methods with a greater advantage. At last, we give the ROC curve comparison. It can be seen that our ACM-FPN and ACM-U-Net outperform the other selected methods. Our code, trained models, and our contributed datasets are available online. Thank you for watching.